Today's problem was submitted by a viewer. It comes from the STEP examination, and it says, sketch the graph of the function h, where h of x is the natural log of x divided by x for x greater than 0. Hence, or otherwise, find all pairs of distinct positive integers m and n, which satisfy the equation n to the m equals m to the n. Okay, so I have solved very similar questions, in particular to the second part of this, many times on this channel, sometimes in different, phrasings or different formats. But the key to the question was always about this function h, log x over x. For x greater than 0. Okay. So x is positive. We don't need to worry about negative values of x. So a few things that we want to do before we even do any manipulations of this or take derivatives or anything. There are certain limits which are pretty clear. When x is very large, everything there is positive, but log x grows much slower than x, and so we know that this is going to approach 0 for large values of x. When x approaches 0 from the right-hand side, this becomes very small and is positive. This becomes very large but is negative, and so this thing is going to be approaching negative infinity, like that. When x is equal to 1, this thing is equal to 0, so this is at 1. And now what I want to do is obviously figure out what the behavior of the graph is in between. In particular, how many minima, local minima and maxima does it have? Now I happen to know that there's only going to be one maximum, and I think it happens at E. I don't remember. So h of x is log of x divided by x. I want to take a derivative. H prime of x is derivative of the top times the bottom minus the derivative of the bottom times the top divided by the bottom squared. And I want to know when this is equal to 0. So I have 1 minus log x is equal to 0. This happens when x is equal to e. So there's only one point, there's only one value of x where tangent lines have a slope of 0, and that happens when x is equal to e. I'm obviously not drawing this to scale, but that's fine. So we have a horizontal tangent there, and then we decrease. Let's get rid of that. Decrease and asymptotically approach 0. So that's approximately what the graph looks like. So if I'm looking for solutions to n to the m is equal to m to the n, and I want distinct positive integers that satisfy this, well, if I take a log of both sides, this is m log n is equal to n log m. So on the left, I can divide by m times n. Log n over n is equal to log m over m. But this says that h of n is equal to h of m. Okay. Well, there's clearly no solutions to this for distinct positive integers. If one of the integers is equal to 1, then the function is equal to 0, and it's positive everywhere to the right, so that's not possible. There's no other integer, positive integer, where this function is equal to 1. And then after the number 2, it is strictly decreasing. So if one of the integers is greater than or equal to 2, then we can't possibly end up with the same value because of the function is strictly decreasing to the right of e. I mean, I guess we could see that if I looked at the derivative here. This obviously cancels to 1. If x is greater than e, then this numerator is negative, and so the function is strictly decreasing to the right of e. So this implies h of n is equal to h of m, but this does not happen for any distinct positive integers. So the answer to the second part of the question is there are no distinct positive integers which satisfy this equation. Any pair of positive integers which satisfy this have to in fact be the same integer. Yeah, so I guess I can say no solution with distinct m and n. Yeah, nice problem. The style of this type of problem that I've solved in the past simply says n to the m is equal to m to the n. Find all possible solutions. It didn't give the hint that h of x is equal to log x over x. But also, I mean, yeah, it's funny. This is one of these problems that's sort of stuck with me. Looking at this function h is really now the natural first step I would have taken given this equation anyway. But that's because I've solved similar problems many times in the past, and on more than one occasion ended up actually struggling with the solution. So yeah, nice little problem. Thanks for the submission, and thanks for watching.